Okay. So, by popular demand, I'm doing this truss problem. And there's a couple ways you could do this. I'll be doing it method of sections because that's typically the easiest way. With one like this, you could do cuts and internal forces and find the internal forces in each of these members to finally get the one that you're looking for. But typically with when you get into bigger truss problems, that's kind of a pain because then there's so many trusses you got to do it for, and it gets messy and takes up a lot of paper. So a method of sections is the way I like to go, because typically it's just asking for one of these, right? Like it's just asking for one member, right? Like what are the forces in this one member, or maybe it's a couple, but you can still do sections for that as long as you just make the cut to section it off into the separate sections. Just make your cut just going through the member that you're looking for. So you'll see what I mean by that. But first we need to do a global free body diagram to find reactionary forces, right? So with this problem, it looks like we have a pin up here, and so that's going to give us a reactionary in the X direction and in the Y direction. I just drew them like that arbitrarily. It doesn't really matter how you draw them. But let's make this easier. Let's label these points, right? So if this is A, I'll call this one A, point A, B, blue C, and D. And so in the problem statement, it says, what are the internal forces in A? Well, I'm going to call this AC, actually. That's typically how you'll see members labeled. You'll see them labeled as like this would be BC, this would be CD, this would be member D, BD. So that's how I like to do it, but it doesn't really matter. They're just variables or unknowns, I guess. So either way, let's set up our equilibrium equations and solve for some of these reactionary forces. So, and there's another one here, sorry about that. And it's only in the X direction because this is a roller, so it's free to move up and down. So there's no force keeping it in the Y direction. So yeah, just X direction, right? Because this is moving down, and it's gonna push against the wall that way. So there's gonna be a reactionary force that way. And I kind of don't like how my shadows are looking in this. Like my shadows are all over the place. So maybe this will help. That didn't really help. That helped a little, did it? Maybe. Whatever. Looks like you can see it. So, okay. Actually, I'm just gonna turn my lights on. Yeah. Did that help? I don't know. I can't tell. Whatever. Here we go. Positive moment. I'm doing that way. That was terrible. But, positive moment, I'm going to say is counterclockwise. And so let's sum the moments about, what do you think? What do you think we should sum the moments about? Because where are all of our forces, right? There's one here, there's one there, and there's two there. So that's 4 forces, and we only know one of them. And with one equation, we can only solve for one unknown. So I'm going to sum the moments about B, because when you sum moments, the forces that go directly through your moment, or the point that you're taking a moment about, you can ignore them. They don't matter, right? Because they don't affect the moment at that point. So we're going to do it about B. So sum the moments at B, so we don't have to worry about these unknowns, and we can just solve for that one. Okay, so our forces are going to be this one and that one. So let's set this equal to 0 because it's not moving, hopefully. F, right? So that's going to be spinning this thing about B. It's going to try to spin it clockwise, so opposing our positive sign convention. So we're going to put that in as a negative 107 newtons, right? And then how far is it from B? Looks like 2L, right? I kind of hate working with like when it says L or some shit. It's like, dude, just say like 5 and 10, but whatever. We'll keep it in the how the problem was given, just for the sake of the video. But typically you wouldn't have to. Typically there would be numbers there, so I like that better. But whatever. Let's go. What's the next force? This one, right? Force at A. We'll call that reactionary AX. And that's working in the positive moment, right? Because it's we're going about B, and this is going to try to spin it counterclockwise. So that's going to be positive RAX, and then how far away is it? That we don't know. So how do we find that out? Well, this is L, right? This is 45 degrees, so that means this is 45 degrees, which means that's 45 degrees, which means this is also L there. So it's L distance away. All right. Now we can solve for RAX, right? So solve for RAX, and that's going to be, what is it? Put this on the other side, that'd be positive 107, 2L, and then divide by 1L. So that would get rid of an L, and we'd have, that's not how that works, huh? I gotta actually do this out. I feel so dumb after spring break. Gotta get back into the swing of, school and shit, huh? Okay, RAX times L, and then divide off the L, and RAX is 107 times 2L over L, which is, what is that, 107 times 2? Get out the old shit box, and I should probably be able to, again, figure that out. 214, right? 214 L over L, so those L's cancel, and it's 214. And that's in newtons, so RAX equals 214 newtons. Great, wonderful. So we can label that on here. 214, and the answer showed up as positive when I solved for it, which means I drew this in the right direction, right? Because the only reason I knew to put this in the equation as positive is just because I happened to draw in that direction. I assumed it'd be going in that direction, and that turned out I was right because I got a positive answer. If I had gotten a negative answer, that's fine. Just turn your arrow around and it's a positive answer. So you can kind of mess with that. Turning the arrows around with any which way, it doesn't really matter. The answer is what matters, is what I'm saying. Okay, so now that we have that, and we have this, we can solve for these, right? Because they're acting in the X and the Y direction. So let's go ahead and sum the forces in the X direction. First, you could do either first. I'm just doing X first because it's whatever. And this is a positive 214, right, in the X direction. And then we have another force up here, RBX and RBY up here. And RBX, I drew it in the positive direction, so it's going to be plus RBX, that equals 0. we can solve for RBX, and that equals negative 214, right? So like I just said, what does that negative mean? Well, all it means is that I drew this in the wrong direction, which makes sense because it's the only other force that's acting in the x direction. This one's acting that way, so the other one's going to be acting this way, right? So it was negative, but now I'm going to write it in here as positive because I turned my arrow around, and we can kind of do that as well, right? Like just say the magnitude is what matters. The diagram is where you can see your directions. And our answer is going to be, like, we have to say whether it's in tension or compression, but we'll get to that when we get to the answer. So let's solve for RBY here. Sum of the forces in the y, set it equal to 0. And again, there's only two forces acting in the y, so like this is pretty intuitive. You could just say like, oh, this force is acting down 107 newtons, and the only other y acting force needs to be acting up at the same amount, right? Because that just makes sense. But we'll do it out just because. So we have a negative 107. Did I say 207 when I last spoke about that? I don't know. But it's 107, right? That was given. And then, so that was acting negative, right? That's pushing down, so we're going to put it in as negative. And then we also have, I drew it as down, so I'm going to put it in as negative. RBY equals 0. Solve for RBY, and that would be negative 107. But again, the negative just means I drew my arrow the right way, or the wrong way, sorry. So let's just flip that around and call this 107, right? Okay, cool. Now we got all of our reactionary forces. We know all of our forces acting on this thing, and so now we can make our cut. And I'm gonna do that right here because it's gonna cut right through the one that we're looking at, right? We want to know the forces, the internal forces of this member. And so now we're gonna make another free body diagram, right? Or a free body diagram. This was just the given diagram, which I use as a global free body diagram, you know, because it's already there. You can just kind of toss your forces on there instead of redrawing it. So, but now we're going to make a new one to solve for the internal forces. And so, which side of this cut should we use? It actually doesn't really matter. It's more just a preference thing. Like, what do you think would be easier? And I'm gonna say this side would be easier, just because, like, I don't know, it seems like less angles and whatever. So I'm gonna do that side. So let's draw that down here. We got a thing going like that, and then like this, and then like that, and then like this, right? That's like this thing here that I just drew. Sorry, it's this thing. What is that? And here is our 214 newtons. Here's our also 214 newtons. And then here's our 107 newtons. Okay, cool. And what's cool about doing it like this is you can turn these members here into forces, right? To represent, they're going to be internal forces. So that's, you can just go ahead and do that, like turn them into arrows instead of members. And we'll mark our angles here. These are both 45. And that's 90, of course. So, all right, cool. Now we need to basically do what we did before, right? Like we got a diagram here with our, let's put a coordinate system on here too. This is important. You'll get points off if you don't do that, right? If you don't define your coordinate system. But so yeah, we basically just do the same thing that we did before. And we can find the internal forces here, right? So we're looking for the internal forces in AC, which would be this one. And that is currently unknown, this is unknown, and that's unknown, right? But luckily for us, we know that forces that go through the moment, right, where you're taking a moment about, they don't matter, right? Because they're going through the moment. So since these two are unknown, I'm gonna put a point there, right? That's B from up there, and this is A. I'm gonna sum moments about B. That way it gets rid of these two unknowns and it leaves us only with this one, right? And that's the one we want. So pretty cool, right? Pretty good, pretty easy. So let's do that. Again, I'm making the sign convention the same way, positive as counterclockwise. Sum the moments about B once again. And this time we basically have two forces, right? Because all of these ones cancel out. This one's canceled out, that one's canceled out, and then these two are also, because they all run through B. So we have 214 down here, right? And that's swinging it this way, which is positive. So I'm going to put a positive 214 in there. All right, and what's the distance on that, right? It's L, because that's what we're drawing here. That whole thing is this whole thing. So we got a distance of L, right? That's this distance. I'll put an L there. And we also have the internal force at A, right? So that I also drew going this way, the same way as that one. So it's also going to be positive. We'll just call it A. And or I guess we'll call it AC, right? Because that's what we labeled it. That's what we're looking for. And what's the distance on that? Well, it's the same as this one, right? It's on the same axis there from B. So that's also a L, right? You can see that, right? Okay. Cool. Let's solve for AC. Solving for AC. That's going to give us negative 214L and then divide by L. So AC equals negative 214. Cool. So again, all that means is that this arrow's going the wrong way. So let's just go like that and go like this and go like that. That's what AC is doing. All right, and so the reason why we don't have to find it on the other side as well and like add them together or some shit is because like if you're pushing on something, like I'm pushing on the table here in my fist, the table's pushing up on my fist at the same magnitude that my fist is pushing down, right? Like if I push my fingers together, this one is pushing on my left finger just as hard as my left finger is pushing on my right. So this force is the same on both sides. So that would be the total magnitude there of your internal force. And like I said, we can just make that positive 214 newtons because I switched the arrow. And that's my internal force. And I know in the question, what did it say? It was compressive, right? Yeah. I said it was compressive, but sometimes it doesn't tell you that, and you gotta figure that out for yourself, whether it's in compression or tension. So the way I think about that is like, so look at this force here, right? It's pushing that way onto this pin, right? So let's just zero in on that. If we have two ends of something and the forces in between are pushing on them like that, right? Like you might look at that and think, oh, that's tension, right? Each arrow is going in different directions, so it's like splitting apart, and you'd think that'd be a tension thing. But really what's going on is these arrows, they're pushing against these two pins, right? Or points on whatever your problem is. So it means that those 2 points on either side are trying to push it in, right? Because these forces have to try to push it out. Like imagine like standing in a doorway and you push on either side of the doorway, right? Your forces would be acting this way, right? Like that'd be your doorway, and your arms you'd be pushing that way, and you'd feel compression in your body, right? Or like, what's another, like if you have two people on either side of you and they're both pushing on you like this, then you're counteracting those forces pushing the other way, but like you're still feeling compression, right? So that's how I think about it. I don't know how clear that was, how well I described that, but our answer is member AC, internal forces, equal 214 newtons, and that is a compressive load. That's how we denote that, is just with a C in parentheses like that. So put a box around her. Boom, that's our answer.